Now that we've explored the inner solar system, we're going to move on and begin to get familiar with the outer solar system. We're going to do that over the next 3 lectures by exploring 1, the Jovian planets themselves, 2, the moons of the Jovian planets, and then 3, the smaller bodies of the outer solar system, such as comets and Kuiper Belt objects. We're going to see a common thread as we go out to the outer solar system. Of course, you know it's much colder out there, so we're going to see bodies made of gases and ices. So today we're going to start then again with the Jovian planets. Let's take a look and get familiar with a few facts and figures. As you see here, we have some very large planets, very different planets than we saw with the terrestrial worlds. Jupiter, Saturn, Uranus, Neptune, composed primarily of gases and ices, very great distances from the Sun. 5 astronomical units for Jupiter, 10 for Saturn, 19 for Uranus, and 30 astronomical units for the planet Neptune. Notice the enormous masses of these worlds. 318 times the mass of the Earth for Jupiter, 95 times Earth's mass for Saturn, 14 and 17 times Earth's mass for Uranus and Neptune. However, notice a much lower density. And again, we saw that the terrestrial worlds are made of very dense rock, whereas these worlds are made of much lower density gases and ices. Well, we know the reason for this. In our previous lecture, we explained that these worlds, again in the outer solar system, beyond that frost line, are again made of much lower density materials. Very different composition, primarily gases like hydrogen, helium, and a few others that we're going to be talking about. Why do these planets get so large? Well, not only was there these gases in addition to the rock and metal that was in the inner solar system, but think for a minute at these great distances of the tremendous volume of material that would be available to build larger planets in the outer solar system. So as a result, the planetesimals that would form out there, whether they be of rock and metal or of ice and gas, there would be far more of them. They could grow larger, and therefore obviously these planets could grow much larger, couldn't they? Well, let's start out by taking a look inside the Jovian worlds, and then we'll proceed to look more at their surfaces and learn more about their atmospheres. Our first diagram shows us the interior, and again, no solid surface to these worlds, completely composed of gas. You can imagine as you would go deeper into the gas, the density would begin to increase, the temperature would begin to increase. We see different layers here within Jupiter and Saturn. Molecular hydrogen, something called metallic hydrogen, which we'll discuss in just a moment. Notice though Uranus and Neptune are a little bit different. These are even farther from the Sun and therefore even colder. And basically they form different forms of water. Now it's very strange water, not like you and I are used to, but in essence it's water. Lower pressures mean that Uranus and Neptune do not have this metallic hydrogen that Jupiter and Saturn do. Let's take a little more detailed look inside, and to do that we'll use Jupiter as our model. Here you see another diagram now showing us the different layers at the surface, hydrogen in its gaseous form. You go a little bit deeper, it becomes more of a liquid in its characteristics, and finally we get to this vast, very strange metallic hydrogen. Why is it called that? Well, the hydrogen here acts like a metal. We know that metals conduct electricity. The pressure here causes the hydrogen to act in such a way. Electrons can move freely. Tremendous electric currents can flow in this region. Very, very strange state of matter. What's at the very center? Well, here we do have some rock and metal. There was obviously a modest amount of that in the outer solar system, and gradually that material again would work its way to the center, where it would form a much denser core. Notice that the core of rock and metal is roughly the size of Earth, but far denser, far more massive. So very, very strange environment as well. Another important fact to realize is that Jupiter, Saturn, and Neptune all generate more heat than they receive from the Sun, and yet Uranus does not. So it's an exception here. And frankly, we don't know the exact nature of that problem and how to resolve that, but we continue to try to learn more and more about these worlds and find a theory that would explain that. Well, that's a brief look inside. Let's go ahead and take a look now at the surfaces, or really the atmospheres of the Jovian worlds. What do we find there? Well, we find that these 4 planets have very strong winds, huge storms, tremendous amount of dynamic activity in their atmospheres. Why is that? Well, there's a number of reasons that we're going to discuss. Let's start out with the composition and the temperature. When we look at these worlds, Jupiter in particular, we see different regions, different bands, so to speak, of different colors. Why is this the case? Well, this is primarily a matter of temperature. You see in our diagram here, at different depths in Jupiter's atmosphere, we encounter different temperatures, and at these different temperatures, different hydrogen compounds will essentially freeze out or condense. The highest layer you see there is cold enough to form ammonia clouds. They tend to be whitish. A little bit deeper than that is a brownish-reddish ammonium hydrosulfide, and deeper than that, cold enough for water to condense and form those clouds as well. So as we look at Jupiter, and we'll extend this to the other worlds as well, again, we see different colors perhaps, and this gives us an idea of the depth to which we are looking at the planet, the composition, and the temperatures. Our next diagram here shows us a comparison of the temperatures. If you look closely, you'll notice temperature increasing to the right, and on our vertical axis, altitude above the cloud tops. And you see, number one, Jupiter's temperature obviously increasing as it goes deeper, and as we just mentioned, different levels, different depths, different temperatures, and therefore we get these clouds of ammonia hydrosulfide, and water. Notice with Saturn, the temperature actually changes similarly, but here the depths of each layer is a little bit different, isn't it? So we're going to see in a future picture here that they're not so obvious, these different levels of Saturn, because we need to try to look deeper, and that's more difficult to do. Notice Uranus and Neptune, though. They don't form these different colors, do they? So we'll see they're primarily a bluish color. Why is that? Well, again, it goes back to their greater distance. At their greater distance, they're far colder than Jupiter and Saturn, and here their atmospheres primarily form methane. Now, methane is a gas that, frankly, makes the planet look blue to you and I when we look at it. The blue light is reflected back to us, the other light is scattered away. So this gives us some idea of, again, not only the interior, but the atmosphere. But let's go ahead and take an even closer look at some of the different features and activities that we do see on these different planets. You may have seen pictures of Jupiter with its tremendously powerful dynamic atmosphere. There's a great deal of activity. Here you see one example of that. Perhaps you're familiar with the famous Great Red Spot. Here you see in the upper right of our image. The Great Red Spot is a tremendous storm system, pretty much the largest in our solar system, much larger than even Earth. It's possible that the storm has existed for several centuries. We have definite observations going back at least 150 years, and it's likely that it was seen even prior to that. Well, where does all this activity come from? As you look at the picture, you see other white ovals there. Those are also storms. You see a tremendous amount of dynamic activity in the atmosphere, obviously very turbulent, very powerful activity. Well, ultimately this comes back to internal heat. Jupiter generates tremendous internal heat, and as a result, these atmospheric features have the energy that are required. Another factor is how the winds on these worlds blow. We think of Earth has prevailing winds in different latitudes. Well, we see something similar on these worlds, but far more extreme. Why is that? Well, you may know that if a world is not rotating very much, air would tend to move from pole to equator and equator to pole, somewhat in a vertical pattern. But it's when a planet rotates that vertical motion is translated into east-west or horizontal motion. Again, we see that somewhat here on Earth to a degree, But here on the Jovian worlds, we see to an even greater degree. And all of them rotate very quickly. Jupiter only takes approximately 10 hours to rotate completely. So as a result, we see tremendous horizontal or east-west bands and zones of wind. Here we have a close-up of some of this. Notice in the lower left, again, those dark and brighter bands and zones. You see if we zoom in, we notice that there's certain regions there where air is rising, other regions where it's falling deeper into the planet. So we do have this vertical development, so to speak, but that fast rotation gives us a tremendous amount of east-west or horizontal winds. You may be familiar with the term Coriolis effect. You may wish to look more deeply into that. This is telling us what's really taking place in Jupiter's atmosphere. So this banding, again, is very characteristic of Jupiter. Now when we look at Saturn, we don't see it nearly as well. Why is that? Well, we said a minute ago that we can't see as deeply into Saturn, and that's where much of that activity would be. So although we do see a little bit of that, it's not nearly so dramatic as it is on Jupiter. When we talked about the terrestrial worlds, we saw that in their cores, molten metal that's moving generates a magnetic field and a region around the planet called a magnetosphere. Is this true for the Jovian planets? Yes, it most definitely is. Here we have much larger planets, and even though there's not so much the field generated in the core, remember we mentioned this region of metallic hydrogen? Well, this vast region has tremendous mass, tremendous currents of material that is conductive and moving due to the fast rotation. So sure enough, Jupiter has an extremely large, extremely powerful magnetic field and therefore magnetosphere, and the other planets as well. Now, as you see in our diagram here, we have a very interesting picture of Jupiter, and it literally shows gigantic aurorae on Jupiter, much as we see on Earth, but in a much vaster scale. So we've seen a number of similarities with the terrestrial worlds, and yet these are very different worlds, aren't they? These Jovian planets of gas, very, very large, very fast rotation, generating tremendous heat. We see great activity in their atmospheres, don't we? Well, we mentioned also at the outset that their vast distances are very dramatic, and that makes them very difficult to study from Earth. How have we been able to study these interesting worlds in recent years? Well, you might know that various spacecraft have visited them. And so I'd like to take a few minutes and just describe a few of those spacecraft missions that have shown us so much about the Jovian worlds. We'll start out with the very earliest spacecraft to go back to the outer solar system. Pioneers 10 and 11, way back in the early 1970s, were sent to do exactly that. Kind of blaze a trail as the first pioneers to go to the outer solar system. They encountered Jupiter in 1973 and 1974, giving us our first close-up views of its tremendous atmosphere. They continued on, Pioneer 10 out of the solar system. Pioneer 11 was actually able to adjust its trajectory to travel all the way to Saturn at that very early stage and give us again our very first close-up view there. A few years later, the famous Voyagers were launched by NASA, Voyagers 1 and 2, in the late 1970s, reaching Jupiter in 1979 and 1980. And these were very sophisticated, powerful spacecraft that gave us tremendous views of Jupiter, Saturn, and as we'll see, also Uranus and Neptune. They not only showed us the planets, but as we'll see in our next lecture, their moons, their ring systems, and so many other wondrous discoveries. I'll give you just a little sample of a few of those. When the Voyagers approached Jupiter, they literally saw one of the moon's erupting volcanoes. We had never seen volcanic activity on another world until this time. Further, they saw an icy shell around one of Jupiter's moons. As they went on to Saturn's moons, they saw one of the moons surrounded by a thick atmosphere. And more things we'll learn in our future lectures. Well, having gone to Jupiter with the Voyagers, they had just flown past Jupiter and Saturn and kept going. Naturally, scientists would like a spacecraft to stay there longer, explore more, take more images and measurements. Well, this was the mission of the Galileo spacecraft during the 1990s. It was sent into orbit around Jupiter, and even though it had a major problem with its main communications antenna, it was still able to return to us tremendous amount of information and pictures and measurements that have kept scientists busy for many, many years. Galileo even carried with it a probe that was dropped into the atmosphere of Jupiter to directly sample and measure its composition, its temperature, pressure. Now you can imagine that probe didn't get too far into Jupiter before the temperature and pressure essentially destroyed it. But it did give us our very first direct measurements of Jupiter's atmosphere. Some years later, scientists wanted to again return back to Saturn. Again, the Voyagers had been there and given us tremendous images, but they wanted an orbiting spacecraft as well. Well, this became the mission of the Cassini spacecraft, which arrived in 2004. Cassini has been doing an outstanding job ever since and is still here in 2016 orbiting Saturn, sending back tremendous amounts of information. Cassini also carried with it a probe, this time not to drop into Saturn, but rather into that mysterious moon we'll see in the next lecture, Titan, with its atmosphere. What did Cassini see when it looked at Saturn? Here you see in these diagrams some false color images of Saturn, and we've basically enhanced the contrast of Saturn. You notice the dramatic banding, which is more apparent here, and it was able to measure winds at nearly 1,000 miles an hour. So again, tremendous activity. Our next slide shows us a tremendous storm system that erupted on Saturn in 2011. Here you see the view from Earth on the left, but on the right, Cassini had a front row seat. This storm exploded up into the atmosphere, and Saturn's east-west winds stretched it out for many tens of thousands of miles, literally around the planet. And this gave scientists an opportunity to essentially look deeper into Saturn's atmosphere. Well, finally, what about Uranus and Neptune? We weren't able to send a spacecraft directly there, but as I alluded to, the Voyagers gave us an opportunity to get a spacecraft out there. How is that? Well, you see this interesting diagram here showing that in the 1970s, the four outer planets, the Jovian planets, were in such position that one spacecraft could reach them all. How was that done? Well, Voyager 2's trajectory was chosen in such a way that as it went past Jupiter, Jupiter's gravity redirected it to Saturn. When it reached Saturn, its gravity redirected it to Uranus. And yes, when it reached Uranus, its gravity was able to redirect it to Neptune. What did it see? Well, it gave us our first and really only close-up views of Uranus and Neptune. In 1986, we received this view back from Uranus. On the left, basically a featureless disk, very little activity. And we see that bluish color I alluded to earlier due to the methane. Great measurements were done on mass, temperature, composition, even the ring system of Uranus. Today, when we look at Uranus from Earth with powerful telescopes, we actually do see more activity. It seems Uranus has become more active, possibly because of its position in its orbit, where more of the planet is receiving heat from the sun than it did in 1986. In 1989, Voyager 2 arrived at Neptune and sent this stunning view back, showing a great dark spot, a large storm system, similar to Jupiter's great red spot. Now, understand that Neptune, is tipped 30 degrees on its axis. Well, you can imagine that would make for very strong storm systems and seasons on Neptune. And here again, you see that blue color due to the methane. So Voyager 2 gave us, again, our first and only looks at Uranus and Neptune up close. Well, now that we've gotten acquainted with the Jovian planets, let's review what we learned. Number one, we saw that obviously these are very much larger planets. Out beyond the frost line, there's far more material of ice and gas with which to form these huge planets. We saw that in their interiors, there's different regions, different layers caused by different pressures as you go deeper. We saw that Jupiter and Saturn have this very strange metallic hydrogen inside. Uranus and Neptune primarily are made of various types of water. We saw too that the tremendous rapid rotation of these worlds had important consequences. Number one, on the surface layers we see tremendous activity in the atmosphere, strong storms, powerful winds, and much dynamic activity. Even further deeper though, that rapid rotation meant that each of these four worlds has a very strong, powerful magnetic field extending out in a vast magnetosphere around the worlds. How do we know about these worlds? They're very difficult to see from Earth, but we've sent spacecraft out there now, the Pioneers, the Voyagers, Galileo to Jupiter, and Cassini to Saturn. These have given us close-up looks of these fascinating planets. In our next lecture, we'll move on to discuss the large moons of the Jovian worlds.